Okay, thank you very much for this time and opportunity. I'm glad to be here again with you. Today I will present my work for half of this month. Since I come from mechanical engineering, this work is about the implementation of optimization to mechanical engineering problem. The title is Algorithmic Solutions for Multi-Batch Optimization in Multi-Gate Layer Machines under Hardware Limitation. So in this talk, I will introduce you to multi-gate layer machine or MWM, and then I will explain the MWM optimization problem, and I will share to you our initial work on MWM, and then I will give you an illustration about challenges from MWM operation and hardware limitation. And after that, I will explain to you about our current work on MWM. So MWM or multi-gate layer machine is an automatic weighing and packing machine. It is invented by IIIA in 1972, and it is used widely around the world. So this slide give you an illustration about the importance of MWM. So we have two types of product. This one, water, sugar, and coffee, has a very consistent relation between its volume and its weight. So if we can control its flow rate, then we can measure its weight accurately. The same things cannot be found in products such as meat or vegetable mix. So we don't have consistent relation between volume and weight for this type of product, because they have irregular shape, and the relation between volume and their weight cannot be predicted accurately. So we cannot control the flow rate to portion their weight. So as an illustration, if we weight product manually, we have to compare the product to be weighed with a standard weight. For example, in this picture, we can see that the weight of the product is lower than the weight of the standard weight. So you need to add more product here, and until the position of this indicator is level. So if you add too much, you have to put it up again. So if you do it manually, it will take a lot of time and a lot of workforce. So for industrial environment, we need a solution that faster. So here comes the multi-gate layer machine. The construction of multi-gate layer machine can be seen in this slide. So we have pull hoppers and then weighing hoppers, and above here is the dispersion feeder. So the product will be poured on top of this dispersion feeder, and then it will be distributed on the pull hoppers, and then pull hoppers will transfer the product to the weighing hopper. In the weighing hopper, we have weight sensor, so we can detect the weight of each product in this weighing hopper. So the weighing process is done by using optimization algorithm. So between these numbers, the optimization algorithm will select a combination that have total weight exceeding target weight of the package. For example, in this slide, we choose 1, 2, 4, and 6 hopper. which the total weight is exceeding 500, equal or exceeding 500 grams. The MWM optimization problem can be explained in an integer linear programming model. So the objective function is to minimize the total weight of the package. So in this ILP model, we have several types of product to be weighted, and as this illustration here, it has several product types, and the constraint consists of several constraints. The first constraint is that the total weight of all product must be equal or greater than the total weight of the package. And for each type of product, the weight of each type of product must be equal or greater than the target weight of each product. This is the ILP model for multi-hardware machine. And the existing approach is that right now we have very few academic works dedicated to study MWM characteristic, even though it is used very widely around the world. And most of the applied algorithm was complete enumeration strategy. So the strategy that is used in real world or in the industry is they use complete enumeration strategy. So in our initial work, we use n-colony optimization as the optimization algorithm, and it is implemented in MWM test cases with 1, 2, and 3 types of products. Because all of us in the eco community, I will skip the explanation of this echo. So I will go directly to the result. So the result for test cases with one type of product is very nice. We don't have any problem here. So we use CPLEX as a benchmark for evaluating the result of ACO. So you can see here, in all test cases, CPLEX obtain optimum values. And in this case, we can see that ACO also obtain optimal value.
Just 1 second. Can you explain again what NK and this sigma are?
So N is the number of hopper. We have 16 and 32. The number of hopper in MWM, 16 and 32. And K is the expected number of hopper to be chosen for each weighing process. Sigma is the standard deviation for the instance. So the standard deviation is very small in these instances. So we can see that the ACO can obtain optimum value, and it can obtain in time much shorter than the time needed by the CPLEX. For the test cases with 2 product types, we begin to have several bad results. Bad result, I mean bad result is not on the optimum value. All of this optimum, but we can see that the value obtained by the algorithm here is quite high. We have 7% product weight above the target weight. So the target weight is 500. We have here 535. So we have 7% bonus to the customer. So it is not because the algorithm cannot perform well. We can see that CPLEX obtain this optimum value, but this optimum value is for from my consideration is bad because it gives too much giveaway to the customer. So it will. So in the real life, it will cost the company more product to be waste, or it will reduce their profit. Other thing that we can see in this result is that in the 32 hopper we have several instances where ACO has a quite high running time. So we can see in this case that ACO became it has a hard time to solve these instances. So the next for the next results result in test cases with 3 product types, we can see that for the 16 hopper we have many of the results, even though it is optimal, but give too much giveaway to the customer, so it will reduce the profit of the company. For the 16 hopper, almost all of the results we have we have too high total weight even though they are all optimal. For the 32 hopper, we can see that the total weight found is not very far from the target weight, so it is as expected, because the more hoppers that you have, the more option that you have, the more option that you can choose from, and then we will have better result than the small number of hopper. But here we can see that we have good.
Avís d'emergència. Cal evacuar l'edifici utilitzant la sortida d'emergència més propera. No us entretingueu. Aviso de emergencia. Deben evacuar el edificio. Utilicen la salida de emergencia más cercana. No se entretengan bajo ningún concepto. Attention please. Attention please. This is an evacuation message. An emergency has been reported to the building. Please proceed to the nearest exit and leave the building. Avís d'emergència. Cal evacuar l'edifici utilitzant la sortida d'emergència més propera. No us entretingueu. Aviso de emergencia. Deben evacuar el edificio. Utilicen la salida de emergencia más cercana. No se entretengan bajo ningún concepto. Attention please. Attention please. This is an evacuation message. An emergency has been reported to the building. Please proceed to the nearest exit and leave the building. Avís d'emergència. Cal evacuar l'edifici utilitzant la sortida d'emergència més propera. No us entretingueu. Aviso de emergencia. Deben evacuar el edificio. Utilicen la salida de emergencia más cercana. No se entretengan bajo ningún concepto. Attention please. Attention please. This is an evacuation message. An emergency has been reported to the building. Please proceed to the nearest exit and leave the building. Avís d'emergència. Cal evacuar l'edifici utilitzant la sortida d'emergència més propera. No us entretingueu. Aviso de emergencia.